Yes, very, very warm welcome to all the participants here once again. Okay, right. Okay, so what I'll do, I'll open up the chat message in one of the system. So I'll be keeping an eye on the chat also, so that we can
Uh,
have, yeah.
Just to add, please note that the lectures have, for those who are joining now, the teachers are actually, most of them, it's in a conversational mode. So if you keep on asking questions, if you don't understand, they will be following and responding as well as part of the time. And if something is not very important, during the break, they will answer all the questions. Maybe after 1 hour, sir will take a small break. At that time, you will so any doubts that are there, you can do. So please keep posting on the chat. Don't post questions related to the course. Whatever sir is teaching, post the queries, right? And after the course is over, at around 5:30, sir will stop. And at that time, you can ask any questions. I will be there to personally answer your queries. Yeah. Thank you so much. Sorry for the this thing, sir. Ashwin sir,
No
please
problem, sir.
continue.
No problem. No problem. Those, yeah, there are question on that. So the question is, will you be able to understand straight away if you join this QT-05 without joining any courses from QT-01 to 04? Uh, yeah, I think Sarah has already answered in a way, but let me answer from my end. Uh, so it's not like a completely disjoint the area and the content being covered in each module, but the fact the resource persons keep in mind, since these people are like different people, so they keep things in mind that they need to cover some sort of basics. Okay, so some sort of basics will be covered, so it is not going to be a complete surprise to the participants. Let's say some topic is picked for a particular day, it will not be not completely understandable. It's not like that. You can still understand only few points, like say I would say some 10 to 20%, maybe you might find to struggle to understand, but you can post the message on the chat related to that. So in that way, you can ensure that even after joining QT-05, you can understand the content being covered here in the QT-05. Okay, right? So yeah, right. So yeah, right. So I will be looking at the chat messages, and I would ensure that you people understand whatever I was discussing. Okay, right. So for today, I was asked to discuss a few things. Okay, let me list down what are the things I want to be like. I was asked to discuss and what I will be discussing. Okay, right. So one thing I was asked to discuss is various ways of realizing quantum qubits. Okay, so that is what I was asked to discuss. Okay, various, 1 minute, various, okay, okay, yes, yes, yeah, um, okay, various ways of realizing quantum qubits, or qubits we would say. Okay, right? So we are talking from the QT-01 until QT-04, or per se, if you say you're talking about quantum computing using quantum qubits, right? So the one question we should ask ourselves: how are the qubits are realized in the first place? Okay, for a theoretician, qubit for us as a theory for the on paper, qubit is some theoretically, you can say theoretically. Okay, qubit means what? Something like quantum state. Psyket is simply equal to alpha 0 plus beta 1. Okay, So what is this? It's a superposition state. It's a superposition of two states. Okay. If any entity which can allow to exist itself in two superposition states simultaneously, that is a qubit for you. So on paper, it is written like this, theoretically. But when it comes to physical realization, the physical realization, okay, it's done in the lab, okay, or done in the some kind of a equipment, okay. So there are various ways we can realize the qubit, okay. So some of them, let me list down. Number one, okay, number one is spin qubits, okay. There are various ways of spin qubits. We will come to that. Number two, I was asked to discuss this, okay, right. Number two is ion traps, okay. So number two is ion traps, okay. Number two is ion traps, means you take the ion and you take and trap them in a location, okay. So somehow you trap that, and what happens, they may exist in the superposition state, okay. So that is one kind of a qubit, okay. The other one is the third one, okay, photon polarization. Photon polarization means photon is going to exist in superposition state based on its polarization, that we will be discussing, okay, right. So number three is that. Number four is, okay, there is something called you just take ions, sorry, electrons. You just trap them certain complex, certain number of electrons, trap them three-dimensionally in a location. So it is going to create something called quantum dots. Quantum dots. Okay, just like you trap an ion, you are going to trap an electron, a combination, many electrons. So that is also going to exist in some superposition states. So that is another kind. Okay. So number five, as of now, is most of the companies are actually uh, doing this, are realizing qubits through this. It is called artificial atoms. Artificial atoms, or you can say some transmons. There is a short name for that, transmons. Okay, right. So there is a question here. Sorry to interrupt. Has any PPT been shared? I have not shared any PPT yet, but what I am projecting here, I'm projecting my hands. Hope you can see that. Okay, right. Okay, so there is one more question. I am from an electronic background. Will it be suitable for me? Could you suggest some basic books if not? So it doesn't matter electronics or non-electronics background. So there are books like Nielsen and Chuang for introduction of quantum computing. So I would say that would be a fundamental level book. You can pick it up and then you can go through it. It's a Nielsen and Chuang. It is available on the net. Okay, right. Okay, so even people from computer science with less physics background, they can also understand that Nielsen and Chuang book. They only deal a very basic level physics, which is required. You might have studied in your 11th and 12th standard. Okay, right. Okay, sir. So fine. So artificial atoms is another way of realizing qubits. So these are the 5 ways we can realize. There are other ways also, but with respect to this particular FTP module, we will only confine to these 5 things. Okay, and I was also asked to discuss something called uh, something called single and two qubit quantum gates, that we will be doing for tomorrow. And also there is a theorem which is going to allow you to realize quantum gates, okay, a higher level quantum gates using a lower level as fundamental gates, okay, right? So that is Solovey-Kitow's theorem. So that we will be discussing tomorrow. For today, we will only discuss these 5 types of qubit realizations, okay, right? Okay, so there is a question here by Vishal Sharmaji. How quantum dots work here for quantum computation calculation? Please explain with a simple example, mainly the mathematical stuff. Yeah, we can touch on that. Okay, right? So which one is more stable one among this all the 5 cases? What is the stable means? You may want to know what is the best for doing computation. Okay, so these questions definitely we are going to touch in this sessions. Okay, right? Okay then. So let's start one by one. Okay, the spin qubits. I want to talk about spin qubits, right? So the spin qubits. Okay, so I did prepare some PPT as well. Let me see what I have for the spin qubits. Okay, right? So I say spin half systems. Okay, and electrons and wait a minute. Let me take a pen here as well. Okay, okay. Wait a minute. Yeah. So I can even write here also. So spin-off systems, electrons, and also nuclears, nuclear spins. That is what I say, spin-off systems. Okay. So here in my spin-off systems, this is the slides I have. So let me recollect for the sake of people who are not from the physics background. For them, I'll just recollect a little bit of what is this spin qubits. Okay, right? So I'll just go down to a very, very simpler level, fundamental physics, and I'll bring in what I want to be conveyed for today. Okay, so right. So yeah, there is a question here. I think a very, very basic level. So it will not harm, but to cover that question. Uh, uh, yeah. Okay. Yeah. Just a minute. Yeah, somebody is saying, I think stable means coherence. Yes, you are right. We will connect to that. What is coherence and stable? Explanation wise. What is the difference between bits and qubits? Okay. So Dr. Kishore Rajgaru is asking, so what is this bits and qubits? So like I said, there is no harm in getting back and just cover that question. So others who know, please don't take it otherwise. So okay, so the bits means what? Okay, bits means it's a information is being stored in the form of bits on a classical hardware, classical memory. So how it is being stored? It is stored as a 0 or 1. Okay, so if you just take a magnetic strip on your hard disk, magnetic one roll will be there, one circular disk will be there. On that, the magnetic information of zeros and ones were stored in the form of magnetic moments. Okay, I'll be touching what is that magnetic moments on just now. For the time being, the information is stored on a classical hard disk, means existing existing computers hard disk in the form of zeros and ones. That is a bits for you. It is a classical information. Classical information in the sense it is certain. There is no confusion there, no ambiguity there. Always zeros and ones exist. As if I say, if I keep the system is perfect, it remains to be 0. If I keep it in that way, it will remain 0. Otherwise, it will shift or it will flip. If not, the system is perfect, it remains to be 0 or 1, whatever state I was started with. Okay, right? So that is a bits for you. But interestingly, there is a way I can realize same memory taking 2 numbers on it. Okay, so same memory Okay, storing 2 bits of information in a one go simultaneously. Okay, so in the classical case, what happens? The information is going to be I have to change 0 to 1, I have to wipe out 0 and put 1 there. But when it comes to quantum computing, there exists a quantum memory. Okay, there exists, that is a quantum memory. Okay, on the quantum memory, I am able to store 0 and 1 simultaneously. Now, the question you may ask, how you are going to do? You have to have some kind of other method. So what is that method is, okay, we will touch that today. Definitely you will understand. Okay, so if I take a system, right, for example, you take a coin, a simple coin, you take a coin, you toss. Okay, if you toss a coin, it flips, keep on flipping. After some time it falls down to heads or tail, depending on, right, the choice. Sometimes it falls to head, sometimes it falls to tail. So what you see here, when it falls to head, you say there's a 50% chance it falls to head, 50% chance it falls to tail. So what I mean here is the fair coin has a chance to fall into both states. Okay. Now, if I had to represent that into a mathematical form, I would say 50% it falls in head, 50% in tail. Okay. But at the same time, if you just take atomic system, okay, an atomic system means atomic levels. Okay, there is a nucleus, there is an orbit around, there are orbits. Okay, there are orbits like this. Okay, right? So let's say this is a ground state, one excited state, third, second excited state, and third excited state, so on, right? Somehow, if I'm able to just take a snapshot of any two levels where I am somehow going to put an electron, let's say, in one of the state. Okay, electron is in that particular state. Okay, I can make it to go to excited state by supplying some energy. That is how the Bohr model description is. That is how nature works. Okay. Now the thing is, the electron when it jumps, usually we think that it jumps certainly to the excited state. It is not. It will be excited to an excited state only few times out of several times. Okay. So which means few times out of several times means I can bring in the idea of probability there. What is the probability is some 60% of the time it exists in the excited state. Okay, 40% of the time it remains in the ground state, means unexcited state. So I have a possibility to store the information of two numbers in terms of probability on a same atom, on a single atom. So in that way I can store 2 bits of information on a single atom. So that is the qubit for you. 2 bits stored on a quantum device or a quantum entity is a qubit for you. As of now, that is the main difference between bits to qubits. Okay, and there is something called qdits. QDIT. What is a QDIT is, okay, QDIT, right? So QDIT means I will have multiple states. How many number of states? D number of states. D can be anything, 2, 3, 4, and so on. Let's say I have D is 3, I'm having Q-trits, okay, right? So Q-dit and Q-trit. Q-bit means 2, Q-trit means 2, 3 states. So I have to remove one of the states here. 1 minute. 1 minute, and just take one pause. Hello. 1 minute. Um, just a minute. I'm sorry. Right. So now the electron can jump to the, let's say the ground state is 0, excited state, and second excited state. Now electron can go to the first excited, and if there is energy supplied furthermore, it can also go to the second excited state. So in this way, I have a Q treat for you. Okay. So you can have as many number of quantum states available for an electron. So if you supply the energy sufficient to go to that level, then fine, you can do that. Okay. Right. Right. So now that's a question I hope I answered. Okay, there is one more question. What is the gas, hydrogen or silver for spin generation in quantum computing machines? Oh, right. So yeah, it's depends. So what kind of like what kind of material you would be having for the equipment wise? Okay, what kind of equipment we have, according to that it will be taken. As a theoretician, I can't comment in detail exactly, but usually they take a rubidium atoms. Okay, right, and plasma they take. Okay, right. So yeah, qubits and qubits. What is a qubit is the quantum system with the d number of states. Okay, right. Qubit is a qubit with the d equal to 2 states. Okay, and qubit is with the d is equal to 3 states. Okay. So earlier I have given you what is a quantum state. Quantum state having two states, 0 ket and 1 ket, as a two substates for a quantum system to exist in two states with the alpha and beta as the probability amplitudes. That's a superposition for you. This qubit is a d equal to 2. It's a qubit with the two states. Qubit is d equal to 3 states. Okay, right? Fine. So the most fundamental one is a qubit. The very first qubit is a qubit, and anything after that you can say qubit and quartet. Okay, right? So and so on, and depending 5 states are there, then you can think about d equal to 5. Fine. I hope now that is made clear, because having a clear idea about qubit and qubit or anything quantum states is a very important to understand what is the spin systems in the first place. Okay. So let's get back to the quantum spin qubits. Okay. Now, like I said, I'm going to start with a very fundamental level quantum, it's a classical physics. Okay. From there we can build on. As you guys know, let me take a single wire, current carrying wire. Let's say conducting wire. So conducting wire, let me send a current through the wire upwards. There is a current going upwards. As we all know, and we have gone through our basic science, as there we got to know if there is a DC current, direct current, not an alternate current. Remember, whatever we get in our homes is an alternate current. Means the current flow of charges, for example, electrons are the most flowable things, and charges, ions or positive ions are not, they just only vibrate, but actual work is done by electron, they move. So when it comes to say DC current, a direct current, electrons moves from one point to other point. How do I move? Probably I'll connect a battery. Suppose I connect a battery. Okay, 1 minute. So I have to connect in the other way around. So battery is like this. So there is a connection of on the bottom, there is a connection of on the top, Okay, so let's say this battery is connected, electrons are traveling downwards, remember, and positive charges are moving upwards. So electron is attracted by positive terminal and repelled by negative terminal. That is how the current is constituted in a current carrying wire, a conductor. Okay. Now electrons will be opposite, positive charges will be in opposite direction. Now if I see this current carrying wire, it generates a magnetic field around. Okay, just like a curling, like a rings will be there. Okay, some rings. Okay, rings of magnetic field. Okay, rings of magnetic field, whatever you see, okay, they are like if anything is there in that ring, it will be like it will be acted upon by this magnetic field lines. Okay, now these magnetic field lines are there. How do I know what is the strength? You can just show your thumb and show, like your curling fingers will show the magnetic field around. Away from the current carrying wire, the magnetic field strength obviously reduces because source is if source is near, then the magnetic field is strong. Okay, right. That's another zone of physics. Right now, we will only concentrate on the current carrying wire. Now, I have a current carrying wire. What I'll do, I'll just, instead of having a straight wire, what I'll do, I'll make the wire to ring like this. Okay. So, just for the sake of the understanding, if you want, I can have a battery over here. Okay. Right. So, the current is traveling, positive charge is traveling right side, so likewise, and negative charge is traveling opposite. Now what you see is the wire is just bent into ring. Now as we know, the magnetic field lines were there as circles, you see, like a circles. Now interestingly, what happens, the magnetic field contribution by each circle of this ring, okay, is going to add up, means add up to the center and cancel outside the ring. You can just try yourself. Take a small ring, you show your thumb along the ring and see the curling fingers. They add up inside the ring. They just doesn't add up outside, because outside from let's say, from, if you just take a ring, a large ring, if the current direction is like that, the fingers will be inward going here due to this region. Okay. Similarly, if you just take opposite region, exactly opposite region, small part, right? Even though the distance is far, but this part also is going to contribute at this location. So the magnetic field due to the this left side, so this is the left side, this is the right side. Okay, right side edge, let's say I call it the edge A, edge B. Edge B magnetic field here, right side, is going in. Edge A magnetic field is, that is how they show. Dot with a circle is coming out. Cross with the circle is going in. See, the magnetic field due to the right edge is cancelled by magnetic field due to the left edge. Okay, but inside, if you see, both gets added up. Okay, right? So both gets added up, right? Point. So in that way, what we will see, there is a resulting magnetic field. There will be resulting magnetic field inside the curve, so inside the ring. So that magnetic field will be, let's say the current carrying is anti-clockwise. So the magnetic field all gets added up. There is a strong magnetic field lines coming out from the axis. Okay, so those magnetic field lines are continuous. They are not like originate somewhere, they end somewhere. It's not like that. So they start ejected and comes back and enter from the bottom. Okay, so like that, right? Okay, magnetic field lines ejected and going in the bottom. So what you see as a bar magnet is being created when I have a current carrying wire bent into a circle like a loop. What is happening? I am going to create a north and south magnetic dipole. So what is the magnetic dipole? It's like a bar magnet. So the bar magnet field line starts from the north, enter into the south. Start from the north, enter into the south. This is the magnetic field lines due to a simple bar magnet. Okay, so that is nice. So when I have a current carrying wire bent into a ring shape, it becomes a bar magnet. So now bar magnet has a magnetic moment. Now the question is, what is a magnetic moment consisted of a ring, current carrying ring? Okay, let me show you. Let's say I created a current carrying ring, like a nice circular ring. Let's say its a radius is R. Okay, the current is constituted, means current going through the ring is, let's say, some I. You know what is the relation between current to the charge? Rate of change of current going through a certain point in a given time dt. That is a current for you. You can say I is equal to some q by t. Okay, right? Some charge. Now that is the current. Now a loop is created. What is the area of the loop? Area of the loop is simply pi into r square, pi r square. Now, if you multiply current with the area, what you are going to get is I pi r square, which is actually a magnetic moment. Magnetic moment. Okay. So that will describe what is the strength of the magnetic field. Means it's like a bar magnet, it has a magnetic moment. So usually it is represented as some kind of a double arrow with the north at the bottom, south at the bottom. So magnetic moment is aligned like this. Now, so if you just take a current carrying wire, I can create an artificial magnet. It's a bar magnet. Bar magnet is a permanent, but artificial magnet is a temporary thing. So that is what people use for solenoids. Okay, they take a nice like a wood material or some kind of a rubber material. They just wind the thread, a wire, okay, and connect this wire to some DC current. So what happens? This will become a very strong bar magnet. So field lines will be coming out, going in. Field lines will be coming out and going in. I hope the current direction is okay. So let me see. The current direction is going opposite. Yeah, that's fine. That's fine. Okay. Okay. So now, okay, let me show you. This is a solenoid for you. Now, a current carrying DC current carrying wire is going to create a dipole. Now, the question is, if you just notice inside an atom, okay, inside an atom, if you notice, there is a nucleus, okay, there are orbits around, okay. So what matters for us is a outermost orbit matters, valency orbit matters. Any other orbit doesn't matter for us because probably electrons are paired inside that orbit. So the electrons are of opposite charge, they pair in such a way uh, uh, they are not going to make a lot of dynamical effect. And moreover, there are positive protons inside the nucleus. If the material is conducting material or magnetically responsive material, which means the number of electrons inside the orbits other than valency orbit are just cancelled by charge wise the number of protons inside the nucleus. That is what happens. Suppose, let's say there is a element with atomic number 55. I'm just giving you an example. Some element, okay, 55. So out, it's, let's say it's a conductor. So if it's a conductor, what happens is 54 electrons will be paired inside all the valency orbit, and there will be 54 protons which are positive charge, So 54 electrons, 54 protons enclosed in a shell. For me, if I look it from outside, if I see, what I see is, I see a neutral shell because positive charge of the electron, sorry, protons are neutralized by the negative charge of the electron of equal number. So what I see is a shell with no charge, neutral. But if on the shell, if I have one extra electron, that will appears to me like a electron existing on a neutral shell, and the presence of electron I can easily notice. So that is a conductor for you, that is a magnetic material for you. Now that is the situation which we are talking about, where the electron is revolving in a particular final valency orbit. Now if the electron is revolving in an orbit, means what? It is like a current, direct current. It's a not alternate current. It is going in one direction. So that is a direct current for you. Now what happens if you just take a rotating electron or oscillate like an electron rotating in a ring, is what it constitute a current. Let's say electron is going anti-clockwise. Okay, let me take electron in a clockwise direction. Okay, and current would be in anti-clockwise. Electron is clockwise, current would be anti-clockwise. Now you see current is in a anti-clockwise. If you curl your finger along the current, magnetic moment is created along the axis upwards. Okay, right? So that is what happens when I have a current carrying electron, a wire consisting of one single electron. So the valency orbit of an electron atom, a conducting atom or a material which is magnetically responsive, it is a DC current cap. It's a magnetic moment thing for us. Okay. So now the question is, okay, in a real world scenario, in a classical world scenario, if I have a current carrying wire, I wind up into a ring, I'll have a magnetic moment. Now the question is, I'm not talking about a classical real world, macroscopic world. I'm talking. What I'm talking at a very, very tiny level. What is that? Atomic level I'm talking about. Electronic level I'm talking about. So at that level, what happens? Things are no more certain. Things are no certainty is there. It is always ambiguous. Means always some kind of a fuzziness will be there. I cannot exactly put and say electron is always in a clockwise direction rotating. We can't know that. Electron is always in anti-clockwise. We don't know that. Because the things are so tiny at that level, sometimes electron appears to be in a clockwise direction rotating, sometimes it appears to be in an anti-clockwise direction. That is not certain. Now what I will do, to just make if I make an observation on that electron rotating in an orbit, I see certain number of times clockwise, certain number of times anti-clockwise. Because of that, what happens? I see sometime magnetic momentum of the electron in an orbit is upwards. Sometimes I see downwards. Okay, right? So this I call the spin magnetic moment being up spin, down spin. Okay, right? So when I have things at such a tiny level, at macroscopic level, sorry, microscopic level, okay, right? We cannot say with certainty. It everything becomes probabilistic. Probabilistic. What I mean is, if I perform the experiment to find out whether electron is revolving in anti-clockwise or clockwise, which constitutes it's going to constitute a upspin or a downspin, it is not going to be 100% certain. It is always going to be a combination of both. That I am going to call it as quantum state of an electron, which can exist in two forms: clockwise spin, clockwise rotation, or anti-clockwise rotation, which I am going to represent in terms of magnetic moment, which is up spin, and a down spin. Okay, and I can connect the spin, the magnetic moment. Okay, so here still now I was saying rotation. Why I'm calling spin? I'll come back to that. Okay, so let's say it's like rotation, which is creating a magnetic moment pointing upward and magnetic moment pointing downward. It is going to be two different ways of quantum states for an electron. So we can call it as a zero ket and one ket. Okay, so this is how rotational spin is realized, rotational magnetic momentum is realized. Now coming back to the question, why did I call it as a spin? We'll come to that. So just take a blob of electron, a very low, like I'm just only concentrating on the electron itself. Okay, now as we see in our solar system, as we all know, just Earth not just rotating around the new sun, it is also rotating on its own axis. Okay, that is why we are getting day and nights. Okay, rotating about the sun, we are getting seasons, but rotating about itself, we are getting to see day and nights. Okay, similarly, if you just take an electron, it is rotating on its own axis, about its own axis. Apart from rotating about the nucleus, it is spinning about its own axis. Now, if you see, electron is made up of negative charge. Okay, it's like some kind of a metallic a blob is charged to negative values. Okay, so that is rotating. Now when some charged thing shows some kind of a change in its position, or it moves, or it rotates, it is going to constitute a magnetic moment, just like a current carrying wire creating a magnetic moment. Now the charge of an electron rotating on its own axis is going to create a magnetic moment. Probably this magnetic moment may not be strength wise as equivalent to the rotating electron in an orbit, but still it is there. It is very, very much there. So that is also going to constitute a magnetic moment for you. Okay, right? So probably it is opposite. If I say anti-clockwise direction, the magnetic momentum would be downwards. Okay, south, north. Okay, so here the magnetic moment is created out of a spinning electron. That's why it's called upspin or a downspin. So more than rotational magnetic moment, people always talk about spin magnetic moment. That's why you see upspin or a downspin. So this is a story of an electron for you. And what about nucleus? You see a very large nucleus is there. It can also rotate on its own axis. It can also rotate about its own axis at the center. Probably sun is rotating about its own axis. Okay. Similar way. So nucleus is also rotating about its own axis. It is going to constitute a magnetic moment because positive charge is rotating about its own axis. So that is going to have a positive magnetic moment, which may be slightly larger than electron magnetic moment because nucleus is a larger entity. Okay, so now even if I am going size wise little larger than electron, what I see here is this nucleus is also so tiny in nature. Okay, at a given time, if I just try to notice and make an observation, what I see, sometimes nucleus is upspin, sometimes it is a downspin. Okay, so because of that, again I'm going to have a quantum state for the nucleus. In what form? It is going to have a form of superposition. Okay, it's going to have a upspin plus a downspin. Okay, right? So with what probability? It's all depends on the situation. You have to measure it. So quantum qubit can be realized using an electron spin and a nuclear spin. So this is what people do in realizing a qubit out of it. Okay, right? So mathematically, how did I write? Just simply up spin and down spin. and probability amplitude would be correspondent to the probability. So if somebody asks what is the chance of electron finding or nucleus finding enough spin, you just take a corresponding probability amplitude, you just take absolute square, and you say with alpha square probability electron would be up spin. Okay, with a square probability nucleus will be in upspin. Okay, very simple. Fine. So that is what the spin-based quantum qubit for you, right? So what kind of electrons were chosen, what kind of a nuclei are chosen, it's all the possibility of the equipment capability of in a lab. Okay, right? So when it comes to electron, I don't see a different electrons. All electrons are same. But when it comes to nuclei, it's all depends. Nuclei is a nuclei of a hydrogen atom, nuclei of a helium atom. Okay, so there is something called Rydberg atoms, right? So depending on the size of the nuclei, you are going to have a different capable magnetic moment. So if I want to have a large magnetic moment, a better controllability and all those things, we might choose down the periodic table some different elements. So as a theoretician, I am not be able to comment what is the best choice for a qubit of nuclei qubit. Okay, right? So from overall perspective, we will just compare all the 5 cases which we are going to discuss for today. Okay, right? So that is a nuclear or electron spin for you. And what else we have to discuss? Next thing. So let's say we have done spin qubits. Okay, right? So yeah, is there any figure I have in my PPT? Let me show you. So this is a figure for you, spin qubits, natural two-level quantum states. What are the quantum states? Spin up, spin down. So when it comes to mathematically represent giving a tag for them, they will give a tag for magnetic spin quantum number. So it is called a magnetic spin quantum number. So usually the electrons are specified inside an atom. Okay, right? So if the electrons are, we have earlier in a figure. Okay, where is the figure? Okay, so here if you say, did I draw one figure? Okay, I might have removed it, I guess. 1 minute. Yeah, yeah, here I have. Here I have. See, the electron can exist in first orbit, second and third and fourth. So where n 1, 2, 3, 4 are called n values, 1, comma 2, comma 3 and 4. So these are called principal quantum numbers. Principal quantum numbers. They specify how far the electron is from the nucleus. Okay, so like the same principal quantum number, there is called angular quantum number L, right? Angular, okay, right? Angular L, with what angular momentum the electron is rotating, okay, and there's a spin quantum number. So similar to that, this is a angular momentum, rotational spin quantum number is there. This is actual spin quantum number, whatever I was projecting in my PPT. So this ms value is specified as plus half and minus half. Plus half correspond to spin up, minus half correspond to spin down. In fact, this plus half and minus half are specified in terms of Planck's constant, H cross. Okay, so probably you will come across that later when you talk about doing computing with the spin-based quantum numbers. Okay, sorry, quantum systems. Okay, that is a spin off for you. Now, if you notice, there is a Q features here. Manipulation via precisely controlled magnetic fields. It is done. Okay, as we straightforward, you can get that because it's small bar magnet. If I want to orient this bar magnet as per my wish, okay, so if you see here, go back. If I have a bar magnet like a north and south, I want to convert that into south and north. It was horizontal alignment. Vertical alignment is there. I want to convert. What I will do? I simply put the large bar magnet between a very large artificial electromagnetic field. So let's say I create a north pole here, a south pole here. What happens? North repels and south get attracts. Okay, so north gets attract. What happens? The magnetic movement or the magnetic dipole just arranges like this. Okay, so this arrangement, just a minute. Guru sir. Hello, I'm sorry guys, sorry everyone. Yeah, so we can align the magnetic moment or a magnet depending on our requirement. Okay, so this is rotation. Actually, the magnetic moment, magnet gets rotated. Okay, right? So in that way, we'll just see rotation and arrangement of magnetic as per our wish. Okay, now The question is, when I implement such a rotation, sometimes it rotates, sometimes it doesn't. So in that way also we will see kind of a quantum state being created. Okay, right. So now we can just take a couple of minutes break. I already took a break, okay, myself while on the call, but we can take a break for just taking a breath. Okay, have a sip of water or something. So I'll just go through the questions here, and I will, when we come back, we'll answer those questions. Okay, right? Okay. Yeah, everyone, welcome back. So, like I said, quickly get back to the questions here. I see a few questions. I'll just quickly cover those questions. Yeah. Okay. So, there's a good question by Satish ji. How to measure spin polarization practically? Okay. See, it's a magnetic moment. Okay. A spin is a magnetic moment. If some spin is there, electron spin is there. Okay. If it is rotating, there is a spin magnetic moment, right? It is like a small bar magnet. How do we find the magnetic fields? Okay, it's the strength of the magnetic field. We bring a small compass, very small compass. Okay, the way it aligns, we find out what is the field line. Okay, so that is how magnetic fields are. So in the same way, if I have some probe which is very sensitive to the magnetic field coming or exerted or created by electron spin, if the probe is there, that probe will measure that. Okay, so I need to have very time. So if I'm talking about a single electron, probably will not. I have a collection of electrons, and their magnetic spin is going to be measured. Okay, right? So spin polarization is nothing but polarization means alignment, whether it's upspin or a downspin. So practically, what is the strength of magnetic moment of collection of few electrons will be found from there. They make out what is the polarization of the electron spin. Okay, right? So okay, the next question. For ket 0 state and ket one state. So ket 0, you may say upspin, and ket 1 may be downspin. You can take it other way around. Since we have only two possible cases, ket 0, ket 1. Sometimes you may also take a combination of both ket 0 and 1. That is a superposition for you. You can have a superposition of 0 and 1 with equal percentage, like 50%. It's a diagonal polarization they call. Okay, instead of having a up spin, okay, instead of having a down spin, maybe sometimes it is a up spin, sometimes it's a up down spin. It's a combination. Okay, so that is what equal superposition you may see in the case of some scenarios. Okay, right? Okay, then there is a one more question here. The Deepak Watts asks, what is the difference between spin qubits and superconducting qubits? Okay, and transmon qubit. Okay, that's one question. And second question is, which is the frequency range to operate these things? Okay, remember, spin qubits so far we have covered. Superconducting qubits we are going to cover at the later stage. In that, after covering that, you may compare both of them and see which is the best and what is the frequency range you to operate them. Okay, so please wait for few more minutes. Okay, right. And yeah, which book is a good for, which covers our quantum T series? Yeah, somebody was pointing out, thank you. Quantum Computing and Quantum Information by Michael Nielsen and Isaac Chuang. Okay, how does quantum machine learning help in green hydrogen production system? Is there any significant research on these things? Okay, remember the quantum computing is what? So existing computers are there. Why we are going to quantum computer means, okay. So quantum computer makes a computation much faster when it compares to classical computer. So if I have to find, let's say, for example, okay, I want to generate a kind of a green hydrogen setup, okay, production unit. So what is the equipment needed to generate that? Okay, consisting of various combinations. A particular combination will give certain efficient production. Okay, so by combination itself changes the efficiency. Which combination gives a better efficiency? is a problem of multiple variable analysis. Okay, right? For example, tomorrow weather, why it is going to be windy, why it is going to be drizzling, all those things is actually calculated in terms of some mathematical mode, depending on the existing initial parameters, how that can affect later times. And it's all about a mathematical extrapolated model that is explored. Okay. So when it comes to just dealing with all sorts of this huge number of data and a huge number of parameters, what you will be needing, you will be needing a large computing capacity and large memory processing capacity. Large memory is also required. So the classical computers may fail to do so, even though the large memory you can have, large computing power you can have. If you are able, if you are going to use a classical computing, what you are going to do, you are going to just assess it one by one, part by part, right? You can't do simultaneously everything. So if you computer, quantum computer is given, you can do everything in one shot. Okay, so that is the quantum computer for you. So the quantum computer would allow you to do a search process for a better green hydrogen production system. What system combination is required? You can search and put it together in a much faster way if I use a quantum machine learning technique. Okay, right? So yeah, if you go to the quantum machine learning algorithms, you would see that. Okay, why classical algorithms are much slower compared to the quantum algorithms in particular task. For example, if there is a data is there, it's unstructured data. If I have to pick an element from unstructured data, if I use a classical algorithm, it will take some time. But if I use a quantum algorithm like Grover algorithm, irrespective of the data is structured or not, you can pick much speed with higher speed. There's a quadratic speed compared to classical machine learning algorithms. Okay, right? Okay, so then there is a one more question here. Basic question. Uh, which are the more stable qubits? Which quantum processor has shown very effective in solving real industry problems? We'll see. We'll probably at the concluding point of today, we may be able to answer that question. Okay. Right. So somebody is from a maths background, trying to learn all the concepts. Okay, well, this suits me. I need to read basic stuff. Stay studying Hilbert space is a key factor here. How to proceed with this means what should I read initially? I miss earlier QTs. Okay, right? So let me tell you, don't bother too much. You can start concentrating on whatever you could extract in today this QT throughout this QT. What I will tell you, please do a little bit of a groundwork. Let's say some topic is said today. If that is you not understood, you quickly go back and search in Google or somewhere, and the short videos are also available on YouTube. You can just check on it. I am not saying you need to thoroughly have QT1 to QT0 for understanding. Then only you need to go. You have to. You should be able to go with QT05. That is not there. Okay, right? So please don't worry too much. For example, you just mentioned about a Hilbert space. Hilbert space is nothing fancy. It is just a vectorial representation of all possible quantum states for a given quantum system. That's all. It's like if I have a two-dimensional surface, let's say X and J, 2D system, all the points on the 2D system are represented by a position vector. So this position vector R, okay, is defined by the base vectors I cap and j cap. Okay, so the I cap and j cap allow me to span the entire two-dimensional surface in a same way. The 0 cat and 1 cat allow me to span all various combinations of alpha, and betas for a given quantum system. Okay, it is just like I can have any value of alpha, any value of beta, provided they sum, their square sum to 1. It's like I am taking a unit circle. Okay, unit circle where x square plus y square is equal to 1. That condition is there. All the points on the unit circle, if I want to represent in one go, I would say these points are represented by a position vector. Position vector is defined by a base vector I and j. Similarly, a quantum system can have all sorts of combinations of alpha with the condition of this. So geometrically, these quantum states are represented geometrically by a block sphere. Okay, any point on the surface of a block sphere is going to have a theta representation, polar angle, and also it is going to have equatorial angle. Okay, so equatorial angle representation it is going to have. So there is a theta and there is a phi representing each point on the surface of a block sphere or a three-dimensional surface is there. Na? So two-dimensional spherical shell on a three-dimensional sphere that is going to represent all the possible points of a quantum system. Okay, right? So that is the Hilbert space for you. So I hope I covered the required. So don't go any more, right? Okay, right. So all right, there is a question here. In which area we apply hybrid algorithms, classical and quantum, both in current industry for a research paper for quantum science students? Yeah, see, you use quantum machine algorithms. Okay, so let's say you have a huge data, for example, which we tried some time back, astronomical data we have. Okay, the galaxies data we have. Let's say you take some astronomical planets. What is the mineral combination? What is the mineral percentage? Okay, so there are observations made by some observatories. They just publish in the net. You take the data. You want to analyze the data. Okay, so while analyzing, you take the data. You see what is the best analysis you could get. Some conclusions you would draw. So to draw a conclusion, classical computer may take some time. Okay, they may take longer time. Quantum computers may do it much faster. Sometimes they're on par. Let's say few seconds, I can say. Let's say sometime if I have hybrid neural networks, where a combination of quantum neural networks is also there and classical neural networks are also there. Combining them, you can create hybrid neural networks. So in this way, you can get the conclusions much faster. So that is a quantum hybrid neural networks for you. So there, the quantum machine learning becomes much more effective. Okay, so let's get back quickly. So we have lost nearly 15 minutes or so, and we need to cover the remaining parts of our various ways of quantum qubits. Okay, so quickly here you see the manipulation of spin qubits done with the controlled magnetic fields, understood, and decades of mature control techniques from NMR, ESR research is a key. Okay, nuclear magnetic resonance based uh, research is being done. NMR based qubits are also being explored. So this is being done in institutes like ISAR Pune. They're using the NMR based qubits to do some tasks. Okay, they were even thinking about doing computing. Okay, right. So mainly they are working on some kind of a magnetic probes. Now, natural two-level systems with intuitive qubit mapping. So spin qubits. Okay. So implementation example, like somebody was asking. So NMR quantum computing using molecular ensembles. Okay. Right. So not a single electron or a single nuclei. they may be taking a molecule, remove some kind of electrons out of it, they may become positive ions. So those molecular ions may show some kind of a rotation effect on their own axis, that is going to be used for realizing spin moments. Okay, and silicon spin qubits. Okay, right? Which one used? And donor atoms in semiconductor matrices. So in the semiconductor material, okay, electrons are donated and these things become holes, right? Okay, right? Extrinsic semiconductors or intrinsic semiconductors, that is the solid state physics for you. There, right, you usually dope host with some kind of a donors where electrons are donated, they become a positive ions. Okay, so those ions may become spin B qubits as they rotate on their own axis. Okay, fine. Now let's go to the next kind of a atom. So next kind of a qubits. The next kind of a qubits is photon polarization qubits. Okay, right? So just to understand what is that in the first place. Okay, if you recollect what is the electromagnetic field for you, electromagnetic field means what? Okay, so if electromagnetic wave, if I say a light is going, right? So if the light is going, electric field is oscillating in a particular direction, let's say vertical direction, right? And in the horizontal direction, you see magnetic field is oscillating. Okay, so this is the electromagnetic field for you, right? So electric field oscillates in a vertical plane, electric field. A magnetic field oscillates in a horizontal direction. Okay, so the polarization of electric field is vertical, polarization of magnetic field is horizontal. Okay, so if you want, I can note down this is a magnetic field. Okay, and the other one is electric field. Okay, so electric field, it's like why it is oscillating, why it is traveling like this. Probably electromagnetic field is generated out of oscillatory dipole. Means there is a nucleus, there is an electron, they come close, they repel each other. So they actually oscillate. When they oscillate, they emit the energy. That energy is electromagnetic wave. So that is an electromagnetic wave that's actually generated from somewhere. We'll not worry how it is generated. Now we'll talk about electromagnetic field having vertical polarization for the electric field, horizontal polarization for the magnetic field. Okay. Now, if I just take a photon, as we know, right, there is a quantization. Okay, very important topic, right? So it was done between 1900 to 1925. Okay, that is the time. There were some experiments were done earlier, like photoelectric effect, like black body radiation, okay, and stability of the atoms. So those are the three basic experiments were done, and people were unable to explain why the results are coming in a particular manner based on existing basic physics were developed back then. So that is the time, okay, the Planck came along. Planck, he said energy is quantized, means the energy travel from one point to other point in the form of bits, like a small bits, like a small entities, is like a pockets. So even though if I'm representing energy of an electromagnetic wave traveling continuously, it is not. How it is traveling? It is traveling in some terms of bits, some kind of a small pockets. Those are called photons. So what is the energy of each photon? Energy of each photon is simply equal to Planck's constant multiplied by, okay, and frequency with which the energy is evolved from a source. So frequency of the source multiplied by Planck's constant will give you the energy of that photon. Okay, fine. So now a photon is an electromagnetic. Maybe it's a very small energy, small disturbance. Now inside that photon, how the electric is oscillating, if you notice, either it will have vertical polarization or it can have horizontal polarization. So a vertical polarization is represented by some epsilon V. If it is a horizontal polarization, it is represented by some horizontal epsilon, where epsilon is a permeability. It's like a polarization. Okay. Now, a given photon can have either a vertical or a horizontal polarization. Okay. Sometimes I can create a combination of both. Okay. So, for example, now light is being emitted from a source. Okay. So, if it's a source is there, it will not have a fixed polarization. Okay. If the light is coming at some point, if you notice, it will have vertical polarization, it will have horizontal polarization, it will also have diagonal polarization, it is also going to have other diagonal polarization. So light will have all the combinations of polarizations. Now what I will do, I want to have a fixed polarization light. What I will do, I use a Polaroid. Polaroid is an entity. It will have a crystallographic axis, something in a particular direction. Let's say its crystallographic axis is vertical. Okay, it's a crystallographic axis. Right? It's something related to alignment of their magnetic moments of individual atoms. That is a crystallographic axis. So they're all arranged in a particular direction. Now what happens? The light goes through that crystallographic axis. Only vertical polarization light is allowed to go through it. All other polarizations were not allowed to go through it. Basically, other polarizations are never interacted with the atoms inside the polaroid. So they just get reflected back or wasted either side. Only the vertical polarization of electric field interacts, that is ejected on the other side. Okay, right? So it's like somebody like standing in a queue passes things. Okay, some passes things in sync. So they throw kind of in the building construction, you see multiple people standing and just transfer things like some bricks. If some inefficient person is there, so the brick may not be continued, it will fall down. Okay, so same here, Polaroid does that. So electric field ejected from the Polaroid is one fixed polarization. If I have a Polaroid with the horizontal crystallographic axis, I'll have horizontal. Now, I can rotate this polarization from vertical to horizontal, or I can rotate by some angle. So what I'll do, I use something called quarter wave plates basically, or half wave plates. They actually manipulate the polarization of the given electric field. So basically, I will change. So what I can do, I can make it between horizontal to vertical. I can have polarization between horizontal to vertical with some angle. Okay. So basically, I use some material which rotates. So in this way, I can create a superposition state photon. Okay. Now, qubit is created. Sometimes, if you just take a photon qubit or a photon, launch it into mirrors, the curved mirrors concave. So, photon is launched in a certain fashion, it goes back and forth. Okay, after some time, you take it out. You can see what is the polarization of outcoming photon because of so many interactions. The photon polarization may have a combinations of horizontal and vertical polarization. So that is a one way of getting. So another way of getting, let's say a light is going with a vertical polarization, people use something called a beam splitter. Okay, so beam splitter is something, it sends the light, half of the light or some part of the light through it and some part of the light reflected. So that's a detector 1, detector 2. So probably the light coming on a D1 and D2 are completely of different polarizations. So basically I created from fixed polarization, I created a different polarization. Probably it's a combination of horizontal and vertical. Okay. So this is how qubits were realized. Okay. Right. So this is a polarized qubits for you. And let's get back what my PPT says for that. Okay. So there are advantages. One is exceptionally low decoherence. Okay. Photon interact weakly with their environment. That's a beautiful thing. Okay. So somebody was pointing earlier, coherence is something to do with the stability. Of course, you are right. Okay. So I intend to keep something, some system in a superposition state of horizontal and vertical polarization for some time. Okay, up to that time, if it exists in a superposition, very good. I'm happy. If not, what I should do? I have to rework and recreate the same photon or some other photon. Okay, so the how much time it can remain intact in my required state is a coherence for you. If something goes out of coherence, is called decoherence. So usually the quantifying thing is people give a decoherence times of a given qubit. Okay, so when it comes to photons, the decoherence time is very low. Sorry, means it decoheres less, so more coherence time. Mainly because the photons are not interact that freely with the environment. For example, spin qubits, if you take, they have like the temperature around the Earth, the ambient temperature may affect greatly this spin qubits. So the uh, system will immediately changes from required state to some other state. So that is why we will lose the chance to control the spin qubits in comparison to photon qubits. Okay. And when it comes to quantum communication and quantum key distribution, quantum cryptography, these polarized photon, light photons are apt, they're ideal. Okay. And beautifully, we can work on room temperature. We don't need to cool cryogenic level for a photonic based quantum qubit computation. Okay. And natural carrier for long distance entanglement distribution. As they have a long coherence time, less decoherence, obviously I can send it to a longer distance. So that's why all the communication using quantum channels is actually done with the photon based qubits. So they are called dynamic qubits, and any other things like electron or spin based qubits or any other qubits are called static qubits. Okay. And obviously, along with the challenges, advantages, there are challenges. One is deterministic two qubit gates remain difficult to implement. Okay, so what it is not that straightforward. If I want to change system from one form to other form and find out in which form they're existing, it's very difficult. That's why people say single photon detectors and single photon sources. As much as difficulty in coming up with single photon detector sources, the same difficulty is there in single photon detectors manufacturing or coming with the innovation. Okay, photon losses in optical fibers limit communication distance. Obviously, there is a loss, means it limits. And moreover, remember, you can't have an amplification effect in the quantum communication because, okay, there is nothing like a quantum amplifier, just like classical amplifier. So you need to do something more. There is something called quantum repeating technology. So it comes in a quantum communication. Okay, and it requires repeaters. That's what I was mentioning. Okay, to have a longer distance communication, you have to basically create some repeating effect. Like say, it's called Bell state. Okay, measurement. Using that, you can extend the entanglement between two points by creating extra entanglement between the further in between points. Okay, so that is a quantum repeating effect for you. So in this way, the quantum qubits were useful in quantum computation or communication per se. Okay, so there is something called for spontaneous parametric down conversion is used to create a quantum entanglement or to create photons of specific polarization. That is a different zone of thing. We are just having an introduction for today. Okay, right. So now coming back to trapped ions and neutral atoms at an atomic scale. Okay, right. So trapped ions. What is a trapped ion? Okay. So ion means having a specific charge. Okay. What I will do, if the ion is there, if I exert a plate, positive plate on one side, negative plate on the other side. If there is an ion, okay, right? If it is a positive ion, let's say some plus some element, okay, what happens? That is repelled by this positive charge, attracted by the negative charge plate. So what happens? Element will try to travel towards the negative plate. Okay. Now I use some when it started traveling. I use some magnetic field from the top to bottom. Okay. Now interesting effect. I'm sorry. When something is traveling inside a magnetic field, you see magnetic field lines goes from north to south. Okay, the velocity is perpendicular to the magnetic field. Magnetic field is this direction, velocity is in this direction. Okay, now if the charge is some q, v cross b is a magnetic force. Okay, what is the direction of this magnetic force? You can use your left hand thumb rule and find out what is the magnetic field direction. So you can create the curling of fingers from magnetic field, sorry, velocity to magnetic field, okay, in such a way that magnetic force can nullify the electric field or electric force. Okay, or what you can do, you can put the magnetic field lines from all the directions, different magnetic poles from all the directions, and electric plates from all the directions. You can create some kind of a area between this entire electromagnetic setup where the electric all the forces were nullifying, and it creates some kind of a tug of war between all the forces. They are all equal, and at some point there is a charge is going to be become stable in that location. So basically you are going to create a trap. Okay, so that is called a ion trap. So with electromagnetic fields it is possible to create a trap. Okay, right? So this is the ion trap for you, right? Now how I am going to realize a qubit out of it? Probably the moment something is trapped, the way it exists in which state, whether it's upspin or downspin state or some location-wise state, or its excitation states. So electron can be excited or de-excited. So the element, ion can be excited or de-excited state. So all those combinations, many possibilities are there to realize the ion trap. Okay, right? So basically the excitations is the means to realize a qubit. So they will find out what are the various orbital levels. Okay, there is something called Zeeman splitting. There is something called Larmor splitting. Means for this element ion, it will have a fixed orbits. Okay, the moment you apply all sorts of this external magnetic field, some orbit splits into hyperfine levels. Okay, I can pick some combination of them to realize a qubit out of it. So basically maybe spin-based qubits, something like that people use to create ion trap based quantum qubits. Okay, and there is something also called, so using lasers also you can create such grooves. What grooves? So I send various lasers like a sequence of lasers, right? See, there are laser lines. There are locations where laser lines are interacting. Okay. So what is this interacting point may create? It's kind of a, we see interference pattern creates a destruction interference and constructive interference. Where there is a destructive interference, we see light is being nullifying, no light there. That is what interference pattern, right? So in the same way, the laser lights actually interacting, creating some kind of a groove, some kind of holes. Okay, some kind of a holes means zero potential location it creates, or negative potential location it creates. If something, some charge is ion is located in that potential, what happens? They remain to exist in the same potential, they cannot come out. Okay, it's like enough a traps that we are creating. Let's say when I have let's say I have neutral atom, I can't use electromagnetic field. What I do, I create a traps where neutral atoms going and falls into that groove and they remain there. Depending on their location, I can get, and depending on their nature, I can get the qubit out of it. So that is a ion traps or atomic traps for you, or optical lattice they call. You see, optical lattice means using a light they create a lattice structure. Okay, so it is for neutral atoms, and a laser control is very much required. So let's see in detail what some kind of facts here. So individual ions are suspended using electromagnetic Paul traps or penning traps. What a trap is created out of a combination of electromagnetic fields from all the directions, not only horizontal and vertical, maybe in a diagonal position also it is created. So you can check on YouTube, sorry, some in the net. There are beautiful pictures are there. I want to put a picture here because the size is too much, so I did not put. There is a nice trap figures. Okay, right. So many experimental labs are working on that. Okay, optical labs I just explained to you using lasers, neutral atoms held by place. Okay, focused laser beams. Okay, they are creating periodic potentials. Okay, right, potential in the sense some kind of a well is created. So there is a infinite potential on the either side, zero potential inside. So if something falls into that, they can't come out, because to come out they have to climb to an infinite height. So this is how the wells, zero potential or lower potential wells, are created using lasers in a periodic manner. Okay, so the precise laser pulses initialize and manipulate and cool and measure atomic qubits. Okay, let's say there is some energy in the atomic qubits are there which may spawn. You can remove that using something called laser cooling. So repeatedly you can remove energy out of a quantum system and put it into a cold form or a stable form. In that way, qubit can be controlled using a lasers. It's called a laser cooling. Okay, right? Okay, so when it comes to few more facts, high gate fidelity means gates can be realized. Okay, those gates can have a very good capability to process the system, and 2-qubit gate fidelity is exceeding 99.99%, having demonstrated using these case qubits. Okay, and long coherence time, very good. This also have a long coherence time ranging from few seconds to few hours. Amazing. Okay, we'll see the combination of all of them in one go, but here the number is seconds to hours. And modular scalability. Okay, the problem is you can't scale them because let's say the Paul traps itself, okay, you can only trap few hundred or at the tens of qubits ions, but not many. Okay, right? So modular scalability is there in this case. Okay, so the industry leaders in this field, IonQ and Honeywell. Honeywell. IonQ is from Canada. Honeywell, I think, continue from UK, and NIST is, I think, from US or China, and University of Innsbruck from Austria. They work on this. Okay, so let me go further. Okay, then somebody was, what is the artificial atoms are transmon based qubits, are artificial and transform based qubits. We'll cover that now. Okay, so yeah, don't worry. I think somebody was asking, is this sessions are recorded? Of course, the sessions are recorded. It will be shared with you all. You can watch it later if something is missed. Okay, right. So, why force acts on a moving charge or ion in magnetic field? So, yeah, it's a very good question actually, right? So, as we know, right, there is a electric field plates, positive and negative. If there is an electron, it is attracted by positive plate, repelled by negative plate. So what is the electric field between positive plate to negative plate? Its electric field is E. What is the force? Electric force is equal to electric field, okay, the charge on the electron, let me say Q, and electric field strength E will give me the electric force, which is moving the electron either left or right. Okay, right? So that means this is what we know. This is our electric force. When it comes to something is moving, let's say there is a magnetic field. Magnetic field is this way. When something is moving this way, right? The curling of V to B, V cross B multiplied by charge, which is moving, is going to constitute a magnetic force. Okay, right? Why it is going to constitute a magnetic force? Very simple. What is that? If there is a current carrying wire, if there is another current carrying wire, so like current carrying wires attract each other, okay, and opposite current carrying wires are repel each other because the magnetic field of some source will have some, if the charge is moving, then only it will have an effect. Okay, right? So if it is not moving, the magnetic field is not going to affect. You know why? Because you see, if a charge is moving, then only it can have a current, then only it can have a magnetic moment. If let's say this charge, let's say the magnetic moment, external magnetic is there, okay, magnetic field lines are going like this, okay. Let's say static charge is there, it is not doing, it is not rotating on its own axis, it is also not moving. If it is not rotating on its own axis, there is no spin magnet movement. If it is not moving at all, it means it doesn't have any current constituted, it doesn't create a magnetic field. What happens? It's a stable thing. Okay, when it is moving, what it constitute? It constitute a magnetic field around, magnetic field lines. So those magnetic field lines respond to this external magnetic moment. When it is revolving like this, it constitutes a magnetic moment like north and south. So that north and south pole small magnet responds to external magnetic field. That is actually constituted in this Lorentz equation. This is a Lorentz force. Okay, I hope that answers. Only when it's moving or showing some rotational dynamics, then only it will have a magnetic moment, then only it will respond to the external magnetic. Otherwise, no. Okay, right. Okay, so I had to go. Why force acts and move? Ah, that is fine. Okay, then coming back to the PPT, right? Artificial atoms. How much I need to have? Okay, this is artificial atoms. Okay, right? Yeah, I'll quickly cover that. So, first of all, to understand the artificial atoms, uh, first of all, we need to know what is atoms. Atoms means what? It consisting of a nucleus. It will have ground state. It will have excited state. It will have higher excited states. Okay, please excuse me with my drawing. I'm in a hurry, so I'll be doing this. Okay, if you see the separation between, wait a minute. The separation between, okay, the ground state to excited state and first excited state to second excited state, energy separations are not equal. Very, very important thing. You see, omega 01 not equal to omega 12. Okay, angular frequency multiplied by h, you will get the energy separation. So this is a naturally occurring atom. By nature, it provides. Nature has a such a thing. It's called non-linear separation. Okay, non-linear separation. The beauty of this one is, let's say I realize a qubit between 0 and 1. Okay, right? If I put an electron here, if I supply a photon of energy separation between 1 to 0, 0 to 1, electron may go here, right? When I say one photon is submitted, I'll not say single photon. I'll have a bunch of photons coming in. Let's say after some time the electron is here, another photon is coming at the time. It can push this electron to some other level if the next level is exactly of same strength. So next level is of exactly equal separation. What happens? The electron may push to the second level. So what may happen? The information may leak to some other level without my control if I have an equal separation between the orbits. But beautifully, I don't have that in natural atom. So I can have natural atoms to create a qubit out of it. But we don't do much. What we do, we use something else, some artificial atoms we do. So why we do is, if you just put an electron in this particular 0 and 1 superposition state, just to go to the next level, no need to even myself give the energy. The ambient temperature around, you see 27 degrees Celsius around this system, or even 1 or 2 degrees Celsius around the system, may push the electron from 1 to 2 and 2 to 3 and so on. It may completely knock the electron out of this entire sector. So in that way, I no more have a control on the electron to have a superposition state at all. So the ambient temperature is around the system is enough to push the electron out of this qubit zone. Okay, so the naturally occurring atom is not fit for realizing a qubit because of uncontrollability. Okay, what people thought, okay, let's take any other system which can show some kind of a quantum states which are separated from one to other. So if you just take a simple LCR circuit, okay, if you just take, there is an inductor, there is a capacitor. Usually there is an internal resistance is there, and some external capacity is there is for the own controllability. Now, if you just take this capacitor, okay, and if you notice, if you supply an oscillatory field, okay, battery source with some battery, some capacitor on the capacitor, what you see, the capacitor charges in different modes. Okay, here I am representing 0, 1, 2, 3. So there is a separation between each state is connected by inductance and capacitance. Okay, it's called impedance. Okay, so what I'm showing here is, so this is a state correspond to a particular state of capacitor being charged to, let's say, some 5 coulomb. The next one is say 10 coulomb. Next one is 15 coulomb. Next one is 15 coulomb, and so on, 20 coulomb. Okay, a capacitor is actually able to exist in any of the 0, 1, 2, 3 states, okay, which correspond to a particular charge states. Okay, now fine, this is okay. So I can take any two kinds of those states and create a qubit out of it. Possible, but the thing is, I'm charging with some oscillatory field. I'm charging continuously. So let's say a capacitor charges to this point. Okay, after some time also the energy is supplied. So coulomb charges are supplied. So capacitor may go to some other state which I don't want to be included in my qubit realization. I want to realize a qubit, it becomes a qubit. So why it is becoming qubit? Because the next state is equally separated from the old state combination. So the information always leaks to some other states uncontrollably, even if I cool the system to 0, because I myself is supplying the energy through some oscillatory field, continuous field. So what people thought, is it possible to make this energy separation or charge separation non-linear? Okay, possible to convert the separation to non-linearity. Let's say question if you ask, people thought initially maybe not possible, but there is a way to do it. What is that is, if you replace the capacitor with Josephson junction. What is Josephson junction? Josephson junction is, You take a superconductor and take another superconductor, sandwich, okay, yeah, a insulator. You do that and you cool the superconductor to millikelvin temperature. You know what happens if you cool it? Okay, if you cool it to millikelvin temperature, what happens is if you cool it to millikelvin temperature, there are electrons gets paired up. Those electrons will jump across even through the insulator. So they do oscillations between back and forth. Those oscillations exist at various frequencies. Let's say the frequencies of mu1, mu2, and mu3, and so on. Those frequencies, some frequencies I can bring in into the circuit, and in a way, induction of that frequencies creates non-linearity in the charge separation of a capacitor. See, if you now see the orbital states, sorry, quantum states of a capacitor is unequally spaced. Now, what I do, I realize a qubit out of any two states. There is no chance qubit may go to some other state, or electron go to, sorry, charge quantum state may not go to other state. So this is called a transmon based qubits. It's called transmon or superconducting qubits or artificial qubits. So how it would look like? It would look like this. So the capacitor, to have maximum capacitance, what they do, they take a capaciting plates not like this. Okay, they will take a capaciting plates like this. Okay, so the other plate is like this. Okay, so that is what you see here. Okay, and you would have internal resistance. Okay, so inductors, they will have some kind of one superconductor, another superconductor. Okay, it's like a, right? So in between there is an insulator. So in this way they'll have capacitor, inductor based transpons. So interestingly, those are, you need to cool it to millikelvin for sure, but we have a better controllability. So that's why people are using a lot this transpon based quantum qubits. Okay, right? So earlier I was mentioning one electron based qubits. If I have many electrons together and put them in one location, confining them into a kind of a trap or not to go anywhere, they may exist in various quantum superposition states. So that is a quantum dot for you. So it's CMOS compatible qubit. Okay, so just like transistors, CMOS transistors, in the same way, you'll have a qubits for you. Okay, so just the details and some challenges are mentioned. Just for the sake of time, what we will jump a little bit into the final conclusion. And if anything is needed to be discussed in detail, we'll do it tomorrow. Okay, so here you see there's some comparison, coherence to gate speed. Okay, so superconducting circuits 1 nanosecond to 1 microsecond, fastest gates you can realize, and shortest coherence time here. When it comes to quantum qubits, 1 microsecond to 100 microsecond, so intermediate range scalability potential. Okay, so the trapped ion, slow gates, and excellent coherence we saw earlier. And spin-off systems, longest coherence, limited scalability. You see, in each one there is advantage, there is a disadvantage. So you need to have a combination, and if people are even thinking about hybrid systems. Okay, so the comparative summary here, if you have, so people are now asking earlier what is a stable. Stable means more coherence time, long coherence time. Okay, it comes with its own weakness, scalable problem. Okay, so proof of concept demonstration, which is done with NMR computing, spin qubits, photon qubits, quantum key distribution is being done, and distance entanglement and quantum networks is being proven. Okay, right? So deterministic 2-qubit gates having not that easy, like a detectors, single qubit detectors, single photon based qubits. But minimal decoherence means more coherence, even at the room temperature. That's the advantage. Okay, trapped ions, superconducting qubits, and quantum dots. You can just see, look at this table here itself, and you can optimize what is the best one with the longer coherence time, what is the best way I can realize the qubits gates. Okay, is there any drawback? According to that, you can plan and get your own qubits. That is what people are doing. So these days, this is more explored, the superqubit, superconducting qubit. Okay, so to answer to many of your question, I would feel superconducting qubits was when it comes to controllability, when it comes to equipment, superconducting is very good. Okay, but when it comes to room temperature, I don't want any cryogenics cooling system. In that case, I will be going with the photonic based quantum chips. Okay, so there is a possibility of hybrid, a combination of all the 3 or 4 cases people are exploring. It's like hybrid network, some photonic qubits, some kind of a transmon qubits. Together they work and they create some hybrid networks. So that is what people are doing and being explored. Okay, right? Okay, so don't worry. I will be sharing the PPT in the Canva. You people go through it and understand. I will also share my hand note, and the recording is also will be shared with you. You can go through it and understand. Okay, right? So yeah, I'll stop at this point. It's already 5:30. So what we'll do tomorrow, we will start at 3 o'clock in advance. Not like today. We'll myself, I'll start the presentation at 3. So we'll end at 3:05. If there is anything to be discussed, we'll discuss tomorrow also. Okay. So thanks everyone for listening. I hope I have already answered all the chat questions. Okay, if there is something is there, we can discuss tomorrow. I'll stop at this point. I'll hand it over to Pillai sir.
Yeah, thank you. Thank you, Dr. Ashwath. Thank you for the wonderful presentation and overview. Material will be available in Canvas, right? Sir will himself load it there, or we will ensure we will also load it once Sir shares with us. So you can get the material from Canvas. So for those who are joining first time, the lectures will be conducted on WebEx. The material and the quiz will be on Canvas, and then we will have the what do you say, communication we can have on WhatsApp. So these 3 links were shared. So hopefully you would have registered on WebEx. That's why you are here on WebEx. You have been part of the WhatsApp, so you can presently it is logged. Now again we'll open after some time. You can check out any questions that are there. Canvas is already login is created for you with the registered ID. You have to ensure that if you don't have it, there are 2 videos which explain how to join Canvas. So please view the video which is there in the confirmation mail. I request all of you to please read the confirmation email. Right? It has 3 parts, A, B, C. Please follow all those 3 parts. Then you can continue. Right? So I hope you have enjoyed. As I told you, Ashwath sir's teaching you will enjoy. So tomorrow we will have the next lecture at 3 o'clock. Yeah, the quiz and other things we will announce. Quiz will be starting from Saturday. You can take on Saturday, Sunday, and Monday till Monday evening. Anytime you start, it will be open for 30 minutes. So within the 30 minutes, you have to attempt the quiz. So that is the issue, but you can take any time, right? There is no need, no feedback form is there. Attendance link is already marked because the time you joined this thing, it will not be one attendance per each login, but we will collect the minutes that you have logged in. So we have written some scripts on WebEx. So it will give us different times that you are logged in and logged out and how much time you are there in the lecture. So that time will be compiled and we'll keep it ready. So for 2,400 hours, we'll take out the ratio and that will be your attendance. So no need for attendance, no need for feedback. We'll collect your feedback towards the end of the session. Thank you so much, Ashwath sir. We'll meet tomorrow. Participants, the group will be open. If you have any doubts, you can ask there. If you have any doubts that are reserved for today's lecture, please note it. Tomorrow, when sir starts the lecture, you can get them clarified. Wonderful time of learning, hopefully. You can actually, yeah, somebody is asking email ID of Ashwath sir. Basically, look up IIIT Dharwad, you will easily get it, or connect with him on LinkedIn. Right? Most of the resource persons are active on LinkedIn and they will actually help you to connect and they will respond to your queries. Right. Thank you so much, sir. A lot of thanks being given for you. So you can just read through.
Thank you, sir.
Yeah. So I will send the schedule, sir, complete schedule, and today I will post it in the group also, and I will send it to you also. Right? We'll take it.
Okay, sir.
Thank you. Thank you, participants. We'll meet tomorrow.